Welcome to the recorded version of the 2021 Advanced SKYWARN Storm Spotter class. I'm Lamont Bain, and I will be taking you through this recorded lecture. There are some advanced topics, and this course does assume that you've taken our basic SKYWARN class. Finally, we ask that you please do not download this presentation due to copyright. Here's a preview of the topics to be covered in this course. We will start off by discussing basic weather radar principles. Then we will talk about some of the base radar products. We will develop convective conceptual models. We'll take a dive into radar signature visual cues. And then we'll attempt to bring everything together with a warning process walkthrough. Let's talk about radar and how it works. Did you know that radar is actually an acronym? It stands for Radio Detection and Ranging. Well, how does it work exactly? Electromagnetic energy is transmitted at microwave frequencies into the atmosphere. Some of this energy is scattered or reflected back to the radar and hits the term reflectivity. Now, in order to sample the complete three-dimensional structure of a target, in this case a storm, the radar will complete a 360-degree sweep. After it has completed this sweep, it will tilt up and complete another 360-degree sweep. Depending on the radar scanning strategy and the range of the targets, the radar will repeat this process an additional 7 to 12 times at higher tilts. Notice how the image on the left changes as our model of the radar on the right tilts up higher and higher. As meteorologists, this information from higher tilts is useful as we can detect things aloft such as hail cores and mesocyclones that may suggest a threat of hazardous weather that may occur in the future at the surface. The image on the left is a composite of all the tilts or elevation angles from a volume scan on April 3, 2012. Now, this allows for the creation of a three-dimensional model of a storm when everything is stitched together. The image on the right is a 2D composite of all the elevation angles. Notice that at higher tilts aloft, the gaps in coverage increases between scans. Note that the radar beam is not a laser. As the beam travels farther and farther away from the radar dish, the beam expands. Now, most of the energy dispensed from the radar dish is concentrated along the radar beam center line, and the power decreases to about half along the outer edges of the radar beam as seen in the top left image. Beam spreading presents our first big radar limitation. Take the example of Storm 1 and Storm 2 in the bottom left diagram. Now, theoretically, they are the same size and contain the same number of targets or raindrops. Storm 1 is closer with a more narrow and confined beam. This allows for a high level of detail in the sample volume. However, Storm 2 is farther away from the radar dish, and with the beam spreading wider and wider, the sample volume is averaged more. As a result, there's a loss of resolution and thus the appearance of a lower number of raindrops, as you can see underneath the volumetric sampling diagram. The beam spreads about 1,000 feet for every 10 miles traveled from the radar dish. So at 120 miles from the radar dish, the beam is roughly over 2 miles wide. You can probably see why this results in a large amount of averaging and a loss of resolution in detail. Now, the second big limitation that we have with the radar beam is the curvature of the Earth. Because the Earth curves beneath the radar beam, the beam height increases with increasing range from the radar. And we'll talk about why this is important in the next slide. Here's our radar coverage across North and Central Texas. The green circles represent where we have good radar coverage below 4,000 feet. The yellow circles represent regions where the lowest elevation that can be detected by the radar is around 6,000 feet. The blue circles represent regions where the lowest elevation that can be detected by radar is 10,000 feet. And the regions with no circles are where radar coverage below 12,000 feet is poor or non-existent. So you can see that this really underscores the continued need for storm spotters, especially in areas like Paris and Palestine, where the radar coverage below 12,000 feet is poor. Now, this doesn't necessarily mean that we can't see targets or storms across Paris or Palestine, but it means that it's a little difficult to detect some of the important signatures below 12 to 14,000 feet. Let's switch gears and review some of the radar products. We will first begin with base reflectivity. Reflectivity, as discussed earlier, measures the amount of energy backscattered or reflected back to the radar after it has hit its target. The units are in decibels or dBz. In general, the more energy reflected back to the radar, the larger the target. In the example to the right, we see a radar reflectivity image from the NWS radar located at the Fort Worth Spinks Airport. Notice some of the pink colors, which indicate either extremely heavy precipitation or hail. As some of you may know, this storm produced greater than 4-inch diameter hail near Wiley in 2016. Our next radar product is the base radial velocity. The most important thing when diagnosing any sort of radial velocity product is to identify the location of the radar. Now, in many instances, it will be denoted as a white dot seen here in the center of the image. From that, examine your color scale and the rest of the image. Now, in general, green or cool colors indicate winds blowing toward the radar. Red or warm colors typically indicate wind flow moving away from the radar. Now, due to the fact that the radar is detecting radial velocity, targets that move perpendicular to the radar are not sampled correctly and will appear to have zero radial velocity. The units of radial velocity are typically measured in knots or nautical miles per hour, and that equates to roughly 1.15 miles an hour. In this example, if we assume the top of the image is more toward the north, we can see that the general wind flow is out of the southeast. However, in the northwest corner of the image, you probably notice an area where air is flowing rapidly toward and away from the radar in close proximity to one another. This implies some sort of rotation and may be an indication of a low-level cyclone. In this case, magnitudes of Doppler velocity toward and away from the radar are both in excess of 80 knots. The base storm relative radial velocity product allows us to account for swifter storm motions that may mask important features. In short, we start with the base radial velocity and then subtract out the storm motion from the radial velocity. Now, the storm's motion on many radar applications utilize either an automated algorithm or storm motion derived from the NWS listed warning text. A few radar applications allow for the user to define a storm motion. By removing the veil that the storm's motion can create, base storm relative radial velocity can make it easier to identify convergence, divergence, and/or rotational signatures. So here is a quick little thought experiment. Why are there two lows in a single storm? We'll sort of discuss some of the different supercell characteristics a little later on in the presentation, and this will answer the question. Next, let's talk about an aspect of radar that has become more popular operationally for the National Weather Service, or NWS, in the past decade, and that's polarimetric radar products. In this lecture, we will often refer to polarimetric radar as dual polarization or dual pol for short. Now, legacy radar transmitted and received EM waves in one plane, and that's the horizontal. Now, with a nationwide upgrade to dual pole, NWS radars now transmit and receive both the horizontal and vertical planes, as seen in this image below. Now, the addition of vertical polarization allows us to compare differences between the two planes, the horizontal and the vertical, and this allows NWS meteorologists the ability to gain further understanding about the targets detected by the radar. Now, the animation below also shows the difference between the legacy, which is on the left, and dual pole radar on the right. We'll review some of these new products in the next few slides. The first dual product that we will talk about is the Differential Reflectivity product, or ZDR. Now, ZDR allows meteorologists to compare the power returned between the horizontal and the vertical pulses. Based on the ratio of horizontal power return to vertical power return, we can infer shapes and, in many instances, the type of meteorological targets. Note the following interpretations of ZDR are only valid for higher wavelength radars, such as those used by the NWS. Dual pole radar signatures on non-NWS radars can be different, especially at those smaller wavelength radars, such as the CASA network. A ZDR near zero indicates that the power returned in the horizontal and vertical are essentially the same, and this suggests that the target is largely spherical, and in many instances, hail. Typically, these types of hydrometeors are hail, or they can be very, very small raindrops. As ZDR becomes larger, this implies that most of the power returned will be in the horizontal plane, and the hydrometeors associated with greater ZDR values are generally larger raindrops. Melting or wet hail, along with oblong hailstones, may also exhibit a higher ZDR. Now, when ZDR falls below zero, it's likely due to ice crystals that tend to backscatter the EM energy more in the vertical plane compared to the horizontal. Here's an example of ZDR when paired with legacy radar reflectivity. As an aside, we always recommend that users use legacy and dual pole radar products in tandem with one another. Now, in this example, we note moderate reflectivity with values between 40 and 50 dBz are co-located with moderate values of ZDR between 1 and 3 dB. This implies larger raindrops on the edge of the storm. Now, if we direct our eyes toward the red and pink or higher reflectivity values, and that's generally greater than 55 dBz, we see that these regions overlap with areas of lower ZDR closer to zero. This increases confidence that this storm has a hail core to the west-northwest of the city of Crum. Our next dual pole product that we will discuss is the correlation coefficient, or CC for short. Now, CC gives the radar interpreter the ability to determine how uniform the radar sample volume is by comparing the behavior of the horizontal and the vertical power returned. Now, unlike ZDR, CC values can be interpreted similarly for all types of radars independent of their wavelength. Now, CC values of less than 0.8 or 80% indicate a high probability of non-meteorological targets. This can be things like biological flyers, buildings, and sometimes even debris lofted by tornadoes. CC values between 0.8 or 80% and 0.97 or 97% imply a mix of meteorological targets. For example, the introduction of hail or other ice particles, especially if coated with water, can lower CC when mixed with rain drops. Now, CC values at or above 0.97 or 97% imply largely uniform meteorological targets in the radar sample volume. So really, the big takeaway from correlation coefficient, or CC, is that it gives us an idea of the uniformity of the radar sample volume. Let's explore an application of CC. As noted with the ZDR example, dual pole products should be examined in combination with base radar products such as reflectivity and/or velocity. Now in the image on the left, we note that the higher reflectivity values are co-located within a region of reduced CC. This implies a mixture of rain and hail. Now the imagery on the right is probably one of the more powerful applications of dual pole radar. From the reflectivity and velocity images, we can see the hook echo and velocity couplet respectively. The addition of reduced CC values in the encircled areas, and these values are more than likely well below 0.8 or 80% here, yields high confidence in a damaging tornado, but again, you've got to utilize the base radar products such as reflectivity and velocity to really utilize DCC. And again, this is probably one of the more robust applications of the dual pole products. Now this example that you see here is from the Dallas tornado back in October of 2019. The final dual pole product that we will review is the specific differential phase, or KDP. Now the gist of this product is that it examines the phase difference between the vertical and horizontal pulses. As EM waves propagate through a set of targets, the vertical and horizontal pulses will become reoriented as it goes through the different phases. The degree in which this phase shift becomes noticeable is really a function of the density of the targets. So this can be useful for things like rainfall estimation. Let's kind of run through a little bit of an experiment here. Imagine we have a sample volume characterized by 50 dBz returns. Now in this first sample volume on the left, a greater concentration of raindrops will result in a higher specific differential phase shift, and this implies the potential for heavy rainfall. Now if we compare this radar sample volume on the left to the one on the right that also has 50 dBz values, but there's a smaller number concentration, it's quite possible that your differential phase will be just a little lower, and this implies a lower number concentration, but because we have the 50 dBz, it's quite possible that we're dealing with bigger raindrops, even though there's fewer of them. So let's step through an application of KDP. We'll also use KDP in tandem with ZDR, which is a pretty popular technique among NWS meteorologists. Of course, always remember to have some sort of legacy radar product when you're interpreting your dual pole radar product. Remember, in general, lower values of KDP that are within regions of larger ZDR imply a small amount of large drops. Remember, lower KDP means less of a phase shift, so likely a lower number concentration of hydrometeors, and higher ZDR typically equates to more oblate particles like raindrops. Now we do see this along the eastern reaches of the forward flank downdraft near Plano and Murphy, as highlighted in the yellow outline. Now conversely, in the instance of high KDP and high ZDR, it's quite possible that we are dealing with a large concentration of targets, and in this example, it's more than likely a lot of raindrops with a potential for heavy rain. Now, it is quite possible that if we're dealing with water covered hail, this also drives up the KDP, the ZDR, as well as the reflectivity. In this instance, we're more concerned with the potential for a heavy rain and possibly marginally severe hail threat in the Addison, Richardson, and Carrollton areas. And this can be seen in the blue outline, where we've got the higher KDP values, the larger reflectivity values, and the enhanced ZDR values as well. As a recap, the legacy and dual pole products must be used in tandem with one another. Legacy products provide details about the storm structure, while dual pole products provide the context to the legacy products. All base products paint a picture of storm scale features, and we can use the base radar data to build a conceptual model.